Hello everyone again and welcome to my channel. So in here we're going to be looking at the intermolecular 3+2 cycle addition, and this is mostly related a little bit to the 4+2 cycle addition. In here we're looking at a species that has 3 atoms that are actually having 4 electrons in them, and that will be involved in a cyclization with another species with 2 atoms containing 2 electrons in them. So now this particular point over here will lead to the formation of a 5-membered ring, and this 5-membered ring is actually visible in this particular product, in this particular reaction scheme over here, where we have heteroatoms within the 5-membered rings. And this is quite interesting how this is being gotten from this particular intermediate process, which has an oxime functional group which we have over here. And this functional group is quite crucial at some point because there will be some kind of an interesting transformation that will make this particular functional group to be ready for the cyclization process in the presence of another reagent, which we'll talk about later. One thing you need to note over here is that this is being formed by the addition of another reagent, which leads to the formation of 2 sigma bonds that are actually like incorporated in this particular process that leads to the formation of this product. On the other side over here, going from this to that is going quite interesting how we need to transform this aldehyde group into this oxime. And what a better way therefore we to be able to look at the reagents that are actually involved in this particular process. One reagent is the process where we use nitrogen with 2 hydrogen atoms attached to the nitrogen, and we have a hydroxyl group attached to this nitrogen, and this is done in the presence of hydrochloric acid, and this is done also in the presence of a base, which is sodium hydroxide. And now once this is included into this reagent, what we need to do then is that this reagent is being transformed into this oxime functional group over there, and what that leads is that we need another functional group, or we need another species that will need to be incorporated to form this final product. And once you notice this, you notice that sigma bonds are formed from another double bond. So this reagent over here will most likely be a triple bonded between these 2 carbon atoms over here. So what that leads is that we have our prop 2 in all, and this is actually this particular reagent over there, where this is a carbon with a carbon over there, triple bond over there, this carbon attached to another carbon, and this carbon is attached to the hydroxyl group over there. And this particular species is mostly called a dipolephile, and this dipolephile is pretty much 8 electron or an electron donating group, because we have a hydroxyl group present over there that donates electrons to this particular triple bond over there. We'll talk more about this particular species in details as we go further, and this has been done in the presence of sodium oxygen with chlorine attached to it, and then in the presence of ET3 nitrogen, and that is kind of a triethylene amide over there. So let's go now in details where we need to transform this into that. So this process is quite easy. Well, I would say it's easy for me perspective, but to you guys it's quite new. But over here we're going to just make this particular functional group over here, or this particular section over here, to be an R group, so I will not waste too much time. So this is equal to R group, so let's just go straight off by just putting the R group. And this R group is attached to this carboxyl group with a hydrogen over there, which is an aldehyde, and then we are including this particular reagent, which is that over there. And take note that this nitrogen is a nucleophile, has a lone pair attached to this carbon, double bond becomes a lone pair on the oxygen, you form electrons, which is negative charge on the oxygen, and then we have hydrogen attached to carbon. This carbon is attached to nitrogen with hydrogen, another hydrogen, and this nitrogen is attached to a hydroxyl group. So take note that in here we have positive charge over there, and now what happens next is that we have water in the system, and this water over here is deprotonated with the presence of this oxygen negative charge, and this extracts hydrogen, and then this single bond becomes a lone pair on the oxygen. And what happens next is that we form an hydroxide, and this hydroxide over there then comes in this process and then extracts this particular hydrogen that's attached to this nitrogen positive charge, and then we have OH group, and take note there's hydrogen over there, and this is the hydroxyl group. This hydroxide extracts this hydrogen, this bond becomes a lone pair on the oxygen, and then what happens next is that we form a lone pair on the oxygen, which makes the nitrogen to be neutral, and in here we have our OH group attached to the nitrogen, carbon attached to the hydrogen, and this carbon attached to the OH group. Now what happens next is that since there's a donating process over here, what that result is that we're going to have this lone pair becoming a double bond between the nitrogen and the carbon. However, what happens then is that this becomes a kind of a good living group which cleaves off, and then what that results is we have the formation of a double bond between the carbon and the nitrogen, and then we have a hydrogen, and note that this nitrogen over here is positively charged, and then we have an OH group over there. Now what happens next is that this OH group that cleaves off comes again with a negative charge and extracts a hydrogen, deprotonating the species and then making the species to be neutral, and this leads to the formation of double bond between the carbon and the nitrogen. And then what happens next is that we have our OH group over there, and this is neutral at some point. So once you have a neutral species over there, and here you have a carbon. Now this neutral species is quite interesting because it forms a 1,3 dipole species over there, and this 1,3 dipole species is as a result of this 1, 2, 3 over here, where we have our 1 end and our 3 end over here being involved in an interesting reaction which either makes it to be nucleophilic or electrophilic. So why am I saying you're going to make one to be nucleophilic or the other to be electrophilic? What this boils down to is the process where we have 3 atoms here that has either the HOMO or the LUMO. That's pretty much interesting as it relates to when it's reacting in the 3+2 cycloaddition. Looking at the orbital overlaps over here, or the orbital model over here, we have the lowest energy state with 3 molecular or this molecular orbital over here. The lowest state is all completely in phase, and then the other side over here, which is the second part, which is the wave function 2. This is our wave function 1. The wave function 2 has a nodal plane over here where this particular orbital over here is orthogonal to both orbitals over there, and this part here is in our phase with this other orbital, and the last part over here, which is the wave function 3, has all the orbitals to be out of phase, where this bottom is out of phase with this, and this bottom is out of phase with that, with 2 nodal planes over there. So what we got over here is that we're going to have either this to be the HOMO over here with 4 electrons distributed between the first and the second, and then this will be our LUMO over here. Now once you have our HOMO, our LUMO, which you have over there, this will either be done or this will be chosen not based on its distribution of electrons over here, but it's going to be based off on the dipolephile. So our dipolephile, which we have in the species over here, we have only 2 possibilities over here. This part over here has only 2 atoms in here, and these 2 atoms are responsible for the distribution of the electrons, which makes it to either electrophile or nucleophile. So the electrophility or the nucleophility of this particular species over here is based on the functional group over here. This functional group, as you know, is an electron donating group, and once it's an electron donating group, this makes this to be nucleophilic because it's going to donate electrons into the system, and nucleophiles are mostly HOMO in its state. So looking at that other part for our triple bonded species, which we have over there attached to electron donating group, or let's just pick two. Either we have an electron donating group or electron withdrawing group, which we have over here. Just an example, and this attached to carbon, or let's just make this to be a triple bond as well. Quite interesting, I'm making that to be a triple bond. But yeah, so maybe this is a triple bond. So in here we're going to have a choice of making this to either be the HOMO or to be the HOMO, or making this to be the LUMO. So in here, what we have over here is that we have the HOMO over here, on this other side over here we have the LUMO. We have the choice of making this to be the HOMO because this is the donating group and donates electrons to this, to make this to be a nucleophile. And making this to be a nucleophile is mostly related to the HOMO state because that is where the electrons are positioned, and which is actually the lowest energy level. On the other side over here we have the HOMO and we have the LUMO, but we have the choice of making this to be the LUMO, and this LUMO is because that we have an electron withdrawing group that removes electrons from this particular region, making this to be electron poor, and this needs electrons at that particular resource. So this will be the LUMO, and this LUMO here will be chosen, while this one here, the HOMO, will be chosen over there. And now once you're able to choose which ones is required with respect to the functional groups that we have in the DIPOLEPHILE, then we'll be able to actually know which one we interact with which in terms of the 1,3 dipole that were generated over here. So in here, since we are using DIPOLEPHILE as the nucleophile over here, where this is a HOMO, so I'll put this to be electrophile, then we're going to use a LUMO, where this orbital will interact with this orbital over there, and that orbital will interact with that orbital over here. Now on the other side, if this, assuming we are using another functional group where the R group is actually electron withdrawing, then we're going to use the LUMO, where this will be in phase, and we're going to use this overlapping with that and this overlapping with that, where the LUMO will interact with the HOMO of the 1,3 dipole. So everything, or this 1,3 dipole, all depends on the DIPOLEPHILE in this case. So let's look at how we're going to transform this particular species over here, which is our oxonium, which we have over here, into our final product in the presence of this species over here. So this over here that we have over here is quite important at some point, because we need to be able to transform it into a much more better electron, or I would say a much more better, this positive with water in it, and we need to make this to generate a species that will be able to give us a better living group. So once this interacts with water, this oxygen over here extracts a hydrogen, and then what you're left over here is an hydroxide over there, and the hydroxide reacts or interacts with sodium to form sodium hydroxide. And then what that gives us then is that it gives us a very important species which you have over there. This important species that we have over here will then be involved in a reaction with this, where it then donates chlorine this particular species donates chlorine to this particular species over here through a particular interesting electron pushing arrows, which we have or is given here below. So we have a nitrogen attached to the hydroxy over there, and what the result, okay, just put this over there. So what happens here is that this hydroxyl with the oxygen over here donates electron to this particular bond over here to form a double bond, and then what happens next is that this nitrogen with lone pairs, the lone pair stays, but then this double bond over here then undergoes a nucleophilic attack and attacks this particular species by extracting the chlorine over there or chloride, and then this bond over here cleaves off to form a lone pair on the oxygen. So what that results is the formation of an R group with the chlorine over there attached to the carbon, and over here the carbon is attached to the hydrogen. On the other side we have a nitrogen, and that forms a double bond between itself and oxygen, and this oxygen has a hydrogen attached, and take note that this oxygen has a positive charge on it. Now, since you know that you have a hydroxide functional group outside there, this hydroxide then comes over here and extracts this hydrogen, thereby deprotonating the species, and then this bond there then forms a lone pair on the oxygen, thereby making this oxygen to be neutral. So what that results is the formation of a nitroso functional group, where we have chlorine attached to the hydrogen carbon, and this carbon attached to the hydrogen, and this carbon attached to the nitrogen. Nitrogen forms a double bond with the oxygen, and this is another species that has a 1,3 dipole state, where this species is actually called a nitroso species over there. And so this nitroso is being formed. What happens next is that we have, or you take note that this sodium hydroxide, which has a hydroxyl group, take note that this hydroxyl group then comes over here again, or hydroxide comes over and extracts a hydrogen, and then what happens next is that this hydrogen bond with the carbon becomes a double bond between the carbon and the nitrogen, and this double bond between the nitrogen and the oxygen then forms a lone pair on the oxygen, thereby forming a negative charge on the oxygen. And what that leads is the formation of this particular product over here. And this product over here is quite fascinating because it's quite related to a particular species that we're about to form, and then that species is actually called a nitrile oxide. So this attacks oxygen with a negative charge. We have a lone pair on the nitrogen, and then we have our sodium stabilizing the negative charge on the oxygen. So what we have next is that since nitrogen donates its lone pair to the system, it then cleaves off this chlorine, because now we are generating a good living group, and this good living group will be leave this particular species because of this lone pair on the nitrogen. So once you form a double bond again, which results in a triple bond between the carbon and the nitrogen, this particular carbon cleaves off from this particular chlorine, and this chlorine actually forms a negative charge outside, and what we get is we form a nitrile oxide species, which is actually that over here. The R group attached to carbon, then we have a triple bond with nitrogen, and this is a linear species over here, or linear functional group over there, and we have our negative charge on the oxygen, and we have our positive charge on the nitrogen. So in here we're going to be choosing what our other species we're going to be used. Our other species that will be used is a triple bonded propyl functional R group that has a donating, oh sorry, this is linear as well, that has a donating group, Let me just shade this to make this look beautiful a little bit. Which is our OH group. So our OH group is the donating group, and as you recall over here that this particular point we're going to be using it to be our HOMO, and once this is our HOMO, then there will be a donation of electrons into this particular species over here, where we're going to have this double bond or this triple bond, one of the bond over here then interacts with this carbon, and then this one of the bond over here then cleaves off and forms a lone pair on the nitrogen, and then oxygen with its lone pair then interacts with this particular carbon, thereby forming sigma bonds over there and sigma bonds over there, making this to be double bond, and here I'm making this part here to become a double bond. So in here we are losing a double bond or we are losing two double bonds or two pi bonds to form two sigma bonds, and this is as a result of the inclusion of this lone pair that has been lost on this nitrogen oxygen to make this oxygen to be neutral. And this part here is actually the LUMO, and this is the HOMO, and the HOMO and the LUMO is dependent on this particular R group over there on the DIPOLEPHILE. So what that results is a 3+2 cycloaddition that gives us our final product, which is this particular structure. Over here, the double bond, which is this double bond, which is that, and this double bond, which is that over here, and then this has been attached to our hydroxyl group over there. So that's about it for this particular reaction on how we're going to be able to generate a 3+2 cycloaddition reaction, and looking at the molecular orbitals that are possible and what are the conditions that you need to understand in order for we to choose which is our HOMO and which is our LUMO, that will enhance the formation of our sigma bonds which we have over here from the two pi bonds that are being lost in this process. All the same, guys, thanks again for following me through this reaction. I truly appreciate it. If you like it, please give me a big thumbs up, subscribe, and share it with everyone around here. Have a good day. Peace, love you all, and be smart.